you very much. Thank you. So today I will give the last lecture of this series. So yesterday we have first introduced Beilinson-Bloch's generalization of height pairing into higher dimensional varieties over number fields. And then we reviewed the Beilinson-Bloch conjecture in various setups, and then introduced the doubling method, the classical doubling method that deal with the central value of the L function. And today we will continue with the discussion in the case where the root number is -1. So yesterday it was 1. Okay. So first, let us recall some setup and notation from yesterday. So recall that n is 2r is an even integer, even positive integer, and we have fixed the CM subfield E with F, the maximal totally real subfield of E. We then equip WR with the skew Hermitian form given by the standard this matrix, 1R negative 1R. And we put GR as the unitary group of WR. This is a split, quasi-split reductive group over F. And for every non-Archimedean field, non-Archimedean place V of F, we denote by KRV, the stabilizer of the lattice OEVN, which is a special maximal subgroup. And yesterday we consider a cuspidal automorphic representation pi of GRAF satisfying the following three restricted conditions. The first one, when V is Archimedean, we require pi V to be a holomorphic discrete series of minimal possible weight. And second, when V is non-Archimedean and non-split, we require pi V to be KRV spherical. And third, we require that pi V is tempered everywhere. In fact, let me just give a remark that actually, under current knowledge, R3 is implied by R1. And so if you assume R1 and assume that pi is in the generic package, then R3 is known. This somehow is related to a question of Raphael yesterday. And yesterday we studied a case where the R times degree of F is even. And this is equivalent to saying that the root number is +1. And today we assume that R times the degree of F is odd. That is, the root number is -1. In this case, we will have another Hermitian space, but not totally positive definite as yesterday. But today it is a standard indefinite Hermitian space V over E of rank n, unique up to isomorphism, that is totally positive definite and split at every non-Archimedean place of V. Okay. So if we check the Hasse invariance, the local Hasse invariance will be +1 at every non-Archimedean place, and will be so if you count Archimedean place, it is exactly also 1, because the changing switch the signature at the default Archimedean place will turn the -1 to +1. So the total Hasse invariant will be 1. So such V exists. And we put H to be the unitary group of V, same as yesterday. I recall that, just recall the notion that V is standard indefinite, means that it has signature n-1, at default embedding, and the signature n0 at other real places. And we also record that for such a standard indefinite Hermitian space V over E of rank n, we have a system of Shimura varieties XL indexed by neat open compact subgroups L of the finite identity points of H, and they are smooth quasi-projective of dimension n-1 over E. And together we have a complex uniformization, which is of this form. Here, this the metric domain is the complex open domain of negative definite lines in the this complex projective space. Okay, these are all just review of some notation from yesterday. So today we will go to the second story. Now we will state some results, some recent results we obtained toward the Beilinson-Bloch conjecture for unitary Shimura varieties. We need to introduce a little bit more notation, which haven't appeared yesterday. So first we will denote by sigma split as the set of places of E that are split in E. Okay, and we denote by sigma lower pi, which is a subset of sigma split, as the finite subset at which pi is ramified. Okay. And since V is split at every non-Archimedean place of F, we can fix an OE lattice lambda such that it is self-dual with respect to this. Somehow it's a rationally self-dual lattice, and we will denote by L0 to be the stabilizer of the completion of this lattice. So this is a maximal special. This is a maximal special subgroup of the finite adelic points of H. This is like the maximal level we will use. And for every finite set sigma of non-Archimedean places of F, we have the following abstract Heck algebra. I denote by T away from sigma, T upper sigma. That is that is algebra generated by this double coset. Okay. And this is, since L naught is special maximal, this is commutative. And it is actually canonical isomorphic to the similar Heck algebra, but for the other unitary group GR, also away from sigma. Okay. And for every finite set sigma of non-Archimedean places of F containing this ramified this sigma pi, we have the Satake homomorphism. I call chi lower pi away from sigma. Oh, sorry, this is not a colon equal, it's just colon. From the T sigma tensor C to C, this is simply the eigencharacter of the action of T sigma. This is a commutative algebra. It acts on the KR sigma. So this algebra is same as this one. So if you take KR sigma invariance, this is a commutative algebra acting on this invariant subspace. There's only one eigenvalue, eigencharacter, and that character we just pi sigma. And we also denote by m pi sigma as the term of pi sigma, which is the maximal of this complex commutative algebra. Okay, so we need to state an assumption that restricts our results. So we propose the following assumption that limits our later theorems. The assumption I call E because it concerns the field E. The field E properly contains an imaginary quadratic subfield E0 in which two splits. Okay, so I want two split in E0, and the discriminant of E0 should be coprime to the discriminant of the totally real subfield F. Okay, and these words properly imply that F cannot be Q. Okay, so somehow this is a technical constraint. We cannot deal with a non-compact unitary Shimura variety at this moment. Theorem. This is a theorem obtained jointly with Charlie. And this is a theorem. We had two papers on this subject, and this one is just the most general one. Actually, not the most general one. What we prove is stronger, but this is the one we will study today. Okay? So assume E. Assume the previous assumption on the field E. If the order of the L function at the center is 1, Okay, in other words, if the central derivative is non-vanishing, then for every finite set sigma of non-Archimedean places of F containing the ramification set sigma pi and contains at least 2 split places. Again, this is another technical condition. At least 2 split places, then we have the following non-vanishing result of the Chow group. So if we localize the cohomological trivial Chow group of codimension R, and you localize at the maximal ideal, because the Heck algebra away from sigma will act on it, because here this L will fix the away from sigma part is fixed. You only change the sigma part. Okay, in some words, we fix the level away from sigma. They are the best level. And at sigma, we consider all possible levels. Then each one will receive an action by the Heck algebra away from sigma. So it makes sense to localize this abelian group, this complex vector space at the maximal ideal determined by this representation pi. And you take all limit, you allow this L sigma vary, and this is non-zero. Okay. So I will explain why this gives evidence toward the Beilinson-Bloch conjecture for unitary Shimura variety. So if we apply the Beilinson-Bloch conjecture for unitary Shimura varieties yesterday to our particular V, and so yesterday there is a V and there is also a pi tilde. Here I take pi tilde to be the theta lift of the pi tilde, the original pi, to the group H. Then this conjecture actually implies that the pi tilde isotypic part of the cohomological trivial part of the Chow group should have dimension 1. So this thing should have dimension 1. However, what we proved is weaker, right? What we prove is that if the isotypic part is non-vanishing, then the localization, of course, is non-vanishing. But what we can prove is weaker than this one. Okay, and passing from localization to isotypic, you somehow need a finite generation of the Chow group if you want to apply Nakayama lemma. However, at this moment, we do not know whether this Chow group is finitely generated as Heck module. Okay? So strictly speaking, this is weaker than this one. But anyway, it's still an evidence. And indeed, okay, here this remark is for people who are familiar with this other endoscopic classification. Okay, so if you remember that in the statement of the Beilinson-Bloch conjecture for unitary Shimura variety, there is a particular isobaric factor of the base change of pi determined by tilde, right? We call this pi, bigger pi tilde. And if you get this statement, you want that the factor that contributes to the order 1 here is exactly from the isobaric factor that corresponds to pi tilde. And this is true. This can follow from some result, I guess, proved by Gan-Ichino, maybe. So the theory of local theta lifting tells us that when this order is 1, okay, so if the order is 1, then there is exactly 1 isobaric factor of the base change of pi that will have order 1. And that isobaric factor is exactly the isobaric factor corresponding to the theta lifting. Okay. So in particular, we do have this version, the first expectation from the Beilinson-Bloch conjecture for unitary Shimura variety. And yes, thus our theorem allies with and provide evidence toward the Beilinson-Bloch conjecture for higher dimensional unitary Shimura varieties. So that's 3 remarks. The last remark, in fact, the theorem we proved is stronger. Okay, so first, we only need a weaker version of assumption E. So in particular, we doesn't really require E to contain an imaginary quadratic field. Okay, but there is a weaker one, but much more technical. So that's why I'd rather to state this stronger but simpler assumption. Second one is more serious. We actually allow more ramification. So here, we somehow only allow ramification at split places. But in fact, we also allow ramification at some certain inner places. So in particular, second, we allow a finite set sigma prime of primes of F that are inert in E, at which pi can be the so-called slightly ramified. Okay, and we formally we call them almost unramified representation. And the upshot of allowing this ramified representation is that this ramified representation will have root number -1 instead of +1. So we will have examples that have -1 local root number instead of this case, instead of this R1 to R3, which only allow us to have negative root number at Archimedean places. So in response, the global root number will be -1 to the R times F, R times the degree of F plus the cardinality of sigma prime. Okay, so in particular, to have a -1 global root number, you don't require R times the degree of F to be odd. You can still have this to be even and this to be odd. Okay, this is a vast relief of restriction of the R and also the field. Okay, but I'm not going to define what almost unramified means. It's a little bit technical, too much in representation. So I will just stay in an easier setup. Okay, any question for remarks and for statement of the theorem?
No questions so far. As far
okay, great. Okay. I hope it is clear. It makes sense for these remarks. So let me give an example of representation pi that satisfies this R1, R2, R3, right? So far, I give no example of this. And so I will give some example that are related, even have arithmetic significance. So we give examples of pi satisfying R1 to R3, also under assumption E, and also under an additional assumption that we require F over Q is solvable. Okay. So we start from an elliptic curve A over Q without complex multiplication, and such that every prime factor of its conductor dA splits in E0. This is same as a Huygens condition, if you remember. So Huygens condition, E0 was denoted by K yesterday. This is like Huygens condition. And by the modularity of A, this is well known. And more importantly, by the recent breakthrough on the automorphic of symmetric power of holomorphic modular forms obtained by Newton and Thorne, there exists a unique, up to isomorphism, cuspidal automorphic representation. I call this big pi sim n-1a of GL and AQ satisfying the following two conditions. So first, the base change of the Archimedean part to GL and C is the principal series of these characters. Recall that R is the argument character. Second, for every prime P that does not divide the conductor of A, the P component of this symmetric power is ramified with the Satake polynomial, and this one. So basically, it's the symmetrical power of the original representation of GL2. Okay, so I'm just writing it down to earth way. So the Satake polynomial is this one, and alpha P1, alpha P2 are the two roots of the original Satake polynomial of the elliptic curve, T squared minus APA T plus P. Okay. And continue. So what we want, our little pi is a representation of a unitary group, not GL and AQ, right? Now we let pi sim n minus 1 AE be the solvable base change. Okay, this is why I require F over Q to be solvable. By the solvable base change of pi sim n minus 1A to the field E. And this remains to be a cuspidal automorphic representation, but now of GL and AE. Okay, so by construction, this representation pi sim n minus 1 AE satisfies the following condition. The dual, the contragradient of this representation is isomorphic to itself, which is also isomorphic to the complex twist. This C is the twist of E over F, the Galois involution of E over F of this representation. And moreover, this RSI L function is regular at 1. Okay, and so these two together will imply that the automorphic representation pi sim AE can be descent to the unitary group. And by the endoscopic classification for quadrisplit unitary groups, there exists a cuspidal automorphic representation, the little pi sim n minus 1 AE of our unitary group GRAF, satisfying R1 and R3. And such that for every place V of F that is not above infinity, not above dA, the base change of the V component of this representation to GL and EV is isomorphic to the V component of this representation. Okay, so in other words, to produce such pi, you only need EDB curve A whose conductor splits in E0. But this is very easy to find. Okay, so you through all this recent breakthrough, you will produce an example, a lot of example satisfying R1 and R1, R2, R3. Good. Now I will introduce question. No.
You assume A is an elliptic curve without complex multiplication. So what will happen if A has complex multiplication?
If it has a multiplication, so first, when A has complex multiplication, the automorphy of symmetric power is known long time ago, but this symmetric power representation might not be cuspidal anymore. I mean, actually, even with complex multiplication, I can still produce pi, but that's not stable anymore. And I have to check whether it descends. I haven't done that. But it is possible that you can still produce more examples, even with complex multiplication. Okay.
Okay.
Okay, good. Mm-hmm. So yesterday, when we reviewed the classical theory of theta lifting, we introduced the theta kernel, right? And the global theta lifting. Today, we will introduce an arithmetic analog of the global theta lifting, which we call arithmetic theta lifting. So we will now state a quantitative version. So we have a theorem here. This is it's not a refined version, right? It only tells you something is non-vanishing. It doesn't give you any height formula or whatever. So we will give a quantitative version of the previous theorem by giving a height formula for an arithmetic analog of the classical theta lifting, which we call arithmetic theta lifting. However, there is a backdraw here is that the construction of arithmetic theta lifting relies on the modularity hypothesis, and a conjecture we introduced lastly in the talk, and this is still unknown when R is greater than 1. Therefore, our height formula is conditional, but the conditional only on the construction of the object. Okay, once you assume it, the proof is unconditional. The conditional is only on the construction of this object. Okay, so from now on, we will assume the assumption E on the field E, and also the modularity hypothesis for V with R equal M. So for your convenience, let me recall what modularity hypothesis mean. So that is, for any Schwarz test function phi fixed by a level L, there exists a necessarily unique holomorphic element, the fancy Z, in the space of automorphic form of weight R, tensor with the Chow group, such that for every finite identity point G, the Ziegel-free expansion of this translation of the fancy Z by G coincides with this formal Q expansion with coefficients given by special cycle with moment matrix T. Okay, I hope you still recall what this is. So each term here is a cycle, is a Chow cycle, and it is even a physical cycle if T is non-degenerate. Okay, but when T is not degenerate, this is just a Chow cycle. Okay, so we will assume the modularity. So here's the definition of arithmetic zeta lifting. Again, for every Schwarz test function phi and every Casper form var phi from the representation pi that has parallel weight R, which is also the lowest weight vector of this representation. I mean, if you are not familiar with this kind of language, you just consider it as a weight 2 modular form. Okay, it's analog of weight 2 holomorphic modular form. So we defined the arithmetic zeta lifting as the following convolution. So yesterday, when we defined the global zeta lifting, we convolute a zeta kernel with the automorphic form, Casper form var phi. Today, we replace the zeta kernel because we're in an arithmetic situation, the zeta kernel is now replaced by, so zeta kernel can be regarded as an automorphic form on GR whose values are in the space of automorphic forms of H. But now this fancy Z can be regarded as an automorphic form still on GR, but with values in the Chow group of the Shimura variety attached to H. Okay, so you change the automorphic form of H to Chow group of Shimura variety associated to H. And then you still, because this is an automorphic form by this hypothesis, this integration makes sense. So you to collapse, so the result will collapse this part. So you get an element in the Chow R XL, but tensor with C, because you have C coming from here. Okay, so that's the definition. So in the definition here, you really need a modularity hypothesis. Otherwise, the integration doesn't make sense. In fact, we prove a little bit more. We can show that this arithmetic zeta lift must belong to the space that is L cohomologically trivial. Recall that, if you still recall from yesterday, that this means all Chow cycles which are absolutely L adequately cohomologically trivial at places away from L. Okay, this guy, for every sufficiently large prime L. Any question with the definition? Okay, if not, let us continue. So yesterday we have this global zeta lifting, and then we immediately state a Rayleigh's theorem concerning the Peterson inner product of the global zeta lifting. Now we have arithmetic zeta lifting, which happens to be an element here. So the natural analog of Peterson inner product should be the Beilinson height pairing. Okay, so we expect to have a formula concerning the Beilinson height pairing of two such arithmetic zeta lift. A story that is parallel to Rayleigh's inner product formula, and we call this arithmetic inner product formula. And this is again joint work with the Chow Li. So we start from two sets of data, a decomposable Schwarz function phi1, phi2, and decomposable vectors of parallel with R from the representation pi. So you have two, the first one, the second one, you have two elements in this group. Now, by the there is a Beilinson height pair on XL. Okay, the sesquilinear extension of the Beilinson height pair we introduced yesterday, and this is the height pair, and we normalize it with the volume of L. This should equal to the product of following terms. First, it is the central derivative of pi at half, and divided by Bn0. And Bn0 is the same constant that appears in the Rayleigh's inner product formula. And we also have those local contribution, the regularized, normalized local zeta, doubling zeta integral. These are same in the Rayleigh's inner product formula. And we have also CR here, and I will introduce some new terms. So first, this volume L is the normalized volume of L in the way that the degree of the Hodge line bundle on XL equals 2 times the inverse of the volume of L. And it is easy to see that the right-hand side, the left-hand side is independent of L. If you don't normalize it, this will depend on L you choose, right? Because if you choose smaller L, you will have a tau map to the original XL, so the volume, the height pairing will increase. So you have to normalize it by this one. So when L gets smaller, this one increases, but this one shrinks. So the product is invariant. So volume L is the normalized volume, normalizing this way. And second, we also need to partially fix the Hara measure, because we are separating, we are explicitating the contribution from Archimedean place. So in the decomposition of the Hara measure on GR, we take the Archimedean one to be the standard measure. So I will not give you the precise definition of the standard measure on URR, but there is a standard one that almost everybody uses that. Okay. The third one is that we also need to partially fix the decomposition of inner product. So in the decomposition of inner product, we want the two vectors to pair with 1 at Archimedean places. Okay. Once you normalize the Archimedean components of this measure and the pairing, then you can actually compute the Archimedean local zeta integral, and that is CR. And I'm not going to give you the volume or the exact amount of CR. That was actually computed by Alan Eischen and Zhejiang Liu. There's some power of pi. I mean, it's a quite a long expression. And the important thing is that the sign of CR is actually -1 to the R. So CR is -1 to the R times a positive real. It is an explicit constant depending only on R. Okay. So as a corollary, you will realize that the left-hand side a priori depends on L and should be an element in C tensor QL over Q. But the right-hand side has nothing to do with L at all. And it's a complex number. So this identity has an implicit implication that this height pairing of this arithmetic zeta lifting belongs to C and is independent of L. So in some sense, we check the part of the Beilinson-Bloch conjecture, Beilinson conjecture on this height pairing for our particular particular cycle, this arithmetic zeta lift. Of course, we want this, right? This should be true for any cycle, but the corollary of this equality is this conclusion. And moreover, if you take phi 1 to be phi 2 and var phi 1 to be var phi 2, then this term and this term are same. And the Beilinson-Bloch conjecture tells you that the sign of this term should be -1 to the R. -1 to the R. Okay. And here, the sign, when you take these two same, this local zeta integral is also positive. So all terms here are positive. Bn0 is positive. And the CR to the f degree f is also -1 to the r. Okay, so this implies that the central derivative should have sign, this should be greater than or equal to 0. That is a consequence of generalized Riemann hypothesis. So this formula is compatible with two bigger conjectures, but we can't prove either of them. But at least this is not contradictory with these two bigger conjectures. Okay, so that's also a sign check. Any questions for this page? Okay. So now we will, in the remaining time, we will explain the strategy of the proof. So just a very, very rough strategy or some idea. So we now fix a sufficiently large prime L. Okay, so in what follows, all height pairing will be with respect to this L. And the strategy is to compare the height pairing. So I'm giving a quotation mark here, and I'll explain what it means, why there is a quotation mark here, between the Kudla special cycle CT1 with the moment matrix T1, and also the other one with moment matrix CT2, and with this derivative. And what is this? Recall that yesterday we have introduced the Ziegler-Eisenstein series on the doubling unitary group G2R, and it has ESG with a Schwarz function on V2R, right? So here is the final part, and at Archimedean part, we patch it with the standard Hermitian Gaussian function on this space, okay? So we do have a Ziegler-Eisenstein series like this, and we regard this function as a function, Ziegler-Eisenstein. Okay, so this one is denoted by this Ziegler-Eisenstein series with value at 1. Okay, sorry, I should say this is this one at G equals 1. I only keep an S variable. Okay, so I only keep S variable, and then I take derivative at S equals 0. Okay, and this T is the, recall that, sorry, it is true. Okay, no. So I denote this curly E as this Eisenstein series as a automorphic form on G2R, and then we have Ziegler Fourier coefficients indexed by T that is a Hermitian matrix of rank 2R, right? And then we take derivative of these Fourier coefficients at S equals 0, and we sum them over those Hermitian matrix with T1 and T2 on the diagonal. Okay. So the height pairing should relate to this one. And this is actually originally a part of the Kudla program. Kudla already observed that there should be such relation. However, there is one difference. So such study was originally proposed in the Kudla program. However, there is a difference is that the height pairing we adopt here will be the Beilinson height. Okay, and the definition of this height does not require any global integral model. Okay, and the original Kudla program is the study of the Gilles-Soulet arithmetic intersection pairing on a nicely chosen model. However, there are several difficulties even before we do this. Even before the start of our comparison, there are 3 major difficulties. The first one, this cycle, CTI, phi I, has no reason to belong to this subgroup of L cohomologically trivial subgroup. So you have no way. If it doesn't belong to here, that doesn't make sense to talk about Beilinson height at all. Difficulty 2, so when Ti is not invertible, it is not when Ti is degenerate, this cycle is only defined as Chow cycle, as we mentioned yesterday. And the Chow cycle is very obscure in terms of height pairing because you don't see it. You don't physically see this cycle. You only know there's a child class. Okay. Difficulty 3. Even when both Ti are non-degenerate, so in this case, these two cycles are well defined as physical cycles in the ZRXL. They may share support. Okay? So these two may have common support. And when they have support, it prohibits us to apply the decomposition formula directly. So recall that there is a decomposition formula for Beilinson height. But before using the formula, you have to choose representative that have disjoint supports. Okay, so it will prohibit us to use this decomposition formula. Okay, so now I'll explain how to solve D1 and D2 and D3. Before doing that, let me remark that by the multiplicity 1 property of local zeta lifting, it suffices to consider L of the following form. So we only consider L to be good away from sigma, and this sigma is a set containing sigma pi and only consists of the split places and has cardinality at least 2. Okay, recall that sigma pi is the subset of sigma split where pi is ramified. Okay, so we only consider L that is good away from a fixed sigma of this form. So how to, oh, by the way, one more notation. I fixed the sigma, okay? And I also put the T as the Heck algebra T sigma complexified. And I denote by chi to be the character, but with respect to pi contragradient. Somehow this is a technical, it's kind of a convention that somehow in the story you should use pi dual rather than pi. And I use M to be the kernel of chi, which is a maximal ideal of this T, okay? So I will suppress sigma in the notation to simplify. Okay, so how to solve D1? To solve D1, we use Heck operators. We show that there exists an element, I denote by little t, in T, but not in this maximal ideal M. And this little t will depend on L, okay? It's not same for any L, such that this T has the following nice property. If we apply T upper star to every such special cycle, the result will belong to this L cohomological trivial part. This is for every I12 and every Ti that is invertible, that is totally positive definite, and every Schwarz test function that is L invariant. Okay, but you will say, okay, how can you just change our Schwarz test function? How can you do that? Okay, well, it just kill anything, can kill everything. The answer is no, because the key point is that the T is not just an arbitrary element in T. It is not in the M. So considering T upper star Z Ti will not lose information toward the arithmetic inner product formula, because at the end of the day, you need to convolute with your cusp form from pi. So when you convolute phi I bar, first you can move T upper star inside to the Schwarz function. Then you can move this T actually to, I missed one step. There's one more equality here. You can also move this T to phi I side, okay? This is a non-trivial result, okay? Sorry, I somehow missed a non-trivial deduction here. You can move T to the phi I side. So when you move T to the phi I side, the action is given by a character, right? By a character chi. And this chi T is not 0 because T is not in M. So chi T is an invertible complex number. So in other words, when you twist this Zt by T, the result will only differ by a invertible complex number. So it will lose nothing toward the inner product formula. Okay, so you're perfectly allowed to do this. But doing this will solve D1. Okay, to solve D2 and D3, we use the same trick. Okay? So we introduce the following notion. So for a non-Archimedean place V, we say that a pair of Schwartz function phi1v, phi2v is a regular pair if the support of their tensor, I mean, second one, I choose it's called a sesquilinear tensor. Tensor is contained in the subset. So this one is a function, Schwartz function on this space. And the support is contained in the subset of elements whose moment matrix is invertible. Okay, this means the moment matrix is invertible. There's a circle here, invertible. This is called a regular pair. And here's a lemma. Suppose that phi1v, phi2v is a regular pair for some v in sigma, then this special cycle indexed by Ti will be trivial will be zero if Ti is not a totally positive definite. Okay, so this solves D2, and the CT1 and the CT2 will have disjoint support for every pair T1, T2 that are both in the totally positive definite Hermitian matrices. Okay, so this little lemma solves both D2 and D3. However, there's a problem. Of course, you can just, the problem is that you cannot, you need to show that there are enough regular pairs, right? If there are very few regular pairs such that if every regular pair will make this local zeta integral vanish, then at the end you are proving a theorem that is 0 equals 0. So it's nothing. So you have to show that there are enough regular pair in the following sense. For every V in sigma, there exists at least one regular pair, phi1v, phi2v, such that the functional var phi1, var phi2 extends to, so you fix phi1, phi2, and then you change var phi1, var phi2, the resulting functional of normalized local zeta integral is non-trivial. Okay, this is the second part of the lemma. And the proof of this lemma is quite surprising. It uses quite a deep Fourier analysis, non-Archimedean Fourier analysis. Okay, so any question about, so I hope it explains how to solve the difficulties D1 to D3. Any question, any confusion?
No question that I can see.
Okay, okay, good, good. So now we go to the analytic side. So how to treat the derivative of Eisenstein series. And the above discussion already provides us with a decomposition, right? We have, because they have disjoint support, there is a decomposition of height into local ones over all places U of E, and over for every pair moment matrices T1, T2, and every pair phi1, phi2 that is regular at some place in sigma. Okay. Now we will provide a similar decomposition for Eisenstein series, the derivative of Eisenstein series, as also twisted by T. So we say that a moment matrix is nearby to V if it satisfies the following two conditions. First, T is invertible. Second, if we denote by Vt, the Hermitian space over E defined by T. So because this is invertible, it will define a Hermitian space, non-degenerate Hermitian space for the Vt. Then the difference between Vt and the V are minimal. In some sense, there exists a unique place, I call the little Vt of F, such that these two Hermitian spaces are same exactly away from this symmetric difference. In other words, if Vt is the default embedding, then Vt and V are same. Otherwise, Vt and V are differ exactly at the default Archimedean place and this place Vt. Okay, this is called a nearby because they are neighbors. These two like are neighbors. So here is the lemma. Suppose that phi1, phi2 is regular at least two places in sigma. That's why we require sigma to have at least two elements. Okay, then this derivative also has a decomposition over places of f. The places of f is by v, and the term here is for each v, the inner summation is going through all Hermitian matrix T that are nearby to V, such that the nearby place Vt is equal to V. Okay, and what is the term here? The term here is phi. Phi is this total Schwarz function. I just put it for short. Okay, I denote it by phi. And the Wt is the T-Siegel-Whittaker function of this Schwarz function. Okay, and I'm not going to give you a precise formula, but this is a well-studied object. But it is also a function in S. There is an S variable, and at V, I take the derivative at S equals U. So if you look at these two, so first you will realize that this Vt must be non-split. Okay, because two Hermitian spaces are always isomorphic at the split places. So Vt must be non-split. So this sum is going over all non-split places. But here, U is going over all places. So this suggests that, so the comparison will consist of 3 types. The first is that if U is above a split place, then there is no contribution here. So ideally, you should prove that there is also no contribution here if U is over a split place of F. And this is our first stage, our first proposition. So for every place U of E of degree 1 over F, we can further find an element SU that is in T but not in M, such that when you translate the cycle again by SU, the height pair is 0. This is true for every pair T1, T2, and every pair 5, 1, 5, 2. That is regular at least 2 places in sigma. And moreover, we can take SU to be 1 if U is not above the original set sigma. Okay, okay. You will ask the same question. You are now changing cycle again. Originally you apply T, now you apply SU. As we have explained, you can always apply Hecke operators from this set. It will not affect the final proof of the theorem. So there is such a freedom. Okay, so this is the first proposition. And the proposition 2 is concerning the places, the non-Archimedean places that are not over split places. So for every non-Archimedean places U of E of degree 2 over F, we have this formula. So volume L times the local height at U is exactly the contribution. So if you compare this term, is exactly those parts here, but only for those T whose diagonal is T1, T2. Okay, so it's this one. Okay? For every T1, T2, and every 5, 1, 5, 2, that is regular at least 2 places. Well, actually, for this one, you only need 1 place. Okay? But this one, you need 2 places. Okay? So these 2 propositions solve the comparison at split places and also solve the comparison at non-Archimedean, non-split places. But there is also Archimedean places, right? We need every place. So there is also a comparison for terms indexed by Archimedean places, but its statement is not just that clean. It's quite technical. So I will not state. Okay. Any question about the comparison? I hope you do believe that this is a comparison for arithmetic side and the analytic side. Okay, and it's a very close comparison. Okay, any question? Good. If no, in the last page, I will quickly explain the idea of the first one, maybe. Okay, and what is involved in the second one? Just very quick words. So we explain the idea for the first proposition of comparison. Now we take a place E of E, or a place U of E of degree 1 over F, and we write V as the underlying place, that is in sigma split. And for every integer m, we denote by LMV, that is a subgroup, that is a unique subgroup of F0, L0V. By the way, L0V is the hyperspecial maximal we have fixed using that lattice lambda, if you remember. Be the unique subgroup such that the quotient is the GLNOF mod V to the m. So in other words, this is the tower of principal congruent subgroups. Without loss of generality, we can just assume LV is some LMV because this is a cofinal in the system of open compact subgroups. Okay, so LMV for some m. Okay. So when MGE is 0, this Shimura variety XLU has a canonical projective smooth model, which I denote by curly L, curly XL. Okay, there's a canonical smooth model. And by the way, the reason we are using model because we want to apply the proposition yesterday to transform the Beilinson local height, which is defined without any model, to certain intersection problem on some nice model, some regular model. And when m is greater than 0, we denote by XL to be the normalization of the above model in XLU. Okay, so when m is greater than 0, there's a map from XLU to the one with m equals 0. Then you turn the normalization of the good model in your smaller level, in your higher level. And it turns out that this XL is regular. Okay, it turns out this XL is regular. And if you remember yesterday about height, there is a last proposition, is that if you have a ring of étale correspondence acting on the model, and you have a maximal ideal that annihilates the cohomology of the entire model, you can easily produce flat extensions of the cycle. And this is exactly the case for our Shimura variety. For every m greater than 0, if you localize the total étale cohomology of the model of degree 2R at the maximal ideal m given by the representation pi, it is 0. Okay. Moreover, if you so this proposition basically allows you to do height pairing using any extension. Okay. Now let's see the curly C just be the TI, just be the naive Zariski closure of CTI in XL. Then this TR per star may not be L flat in general. However, due to this proposition, you can further apply a Heck operator SU that is not in M, such that SU upper star, TR per star of the Zariski closure is L flat. Okay, and then to compute the height, you just take an intersection. But however, the condition that this Schwarz function is regular at least 2 places will imply that even there's a risky closure of the original cycle will have disjoint support on the model. Okay, so previously we just say that their generic fiber have disjoint support, but now this is the feature at split places that even you take Zariski closure, they still have disjoint support. Okay, so if these two have disjoint support, their intersection on the model must be 0. Okay, must be 0. And then since they are L-flat extensions, such intersection number calculates the Beilinson local height by our proposition yesterday. In particular, we proved the first proposition. Okay. And how about second one? And the second proposition of comparison will boil down to a similar comparison for the intersection number of special cycle on a certain reparable think space. And such comparison on the reparable think space is known as a Kudler-Rappaport type conjecture. I mean, actually, when V is inert in E, this is exactly the Kudala-Rapoport conjecture. And then when V is ramified in E, Charlie and I formulated and proved an analog of Kudala-Rapoport conjecture in that setup as well. Okay, but the content of the proof will require another short course, so I will not continue. Okay, thank you.
Thank you very much. Are there some questions in the audience? Yes, there is one here.
Mm-hmm.
Okay, I actually don't know whether this is a reasonable question. I would like to know this in this theorem, you need to assume the weight is parallel to BR. I would like to know whether this is a technical condition or actually is this all we're concerned about?
Theorem, you mean?
Yes,
you mean this one?
Phi 1 and yeah.
You mean here, right?
Oh, yeah.
Okay, actually, so seriously speaking, if you take phi 1 Archimedean to be arbitrary test vector, it is fine, but you just get different Archimedean term. However, most likely that term is 0.
Okay.
Because the point is here, the point is that when you do the theta lifting, you have this term, right?
Yeah.
This term has parallel with R. This cannot be changed. So if this term you don't do parallel, well, you take a convolution, it's 0 most likely.
Okay. So
yeah.
This theta lifting can now see those weights is not parallel.
No. The theta lifting only see the minimal vector. Yeah.
Okay, I see.
The arithmetic theta lifting. Sorry, not theta lifting. Arithmetic generating series. Always the minimal weight. Yeah.
Okay, and for the automorphic representations we are concerned about, we can always take the lowest weight vector, and it will be of parallel weight. Is that so?
Yeah. I mean, you want something that has non-trivial inner product, right? Otherwise, it's 0 equals 0.
Okay.
Yeah,
Thanks a lot.
Yeah.
Are there other questions or comments? And on Zoom? No, there is nothing on Zoom. So so thank you very much. Let's thank the speaker again.
Thank you.